So dear students, so in our last class we have solved one example problem where there were three springs or spring elements, and at the leftmost end or the leftmost node was fixed, and the rightmost node was also fixed. So this was the stiffness matrix, system stiffness matrix. These were the displacements at the degrees of freedom, and these were the forces at the degrees of freedom. Now you must have noticed that U1 is fixed as 0. So U1 is fixed, so it's 0. U4 is fixed and it's also 0. And these are the this F1 at 1 and F2 at 3. These are the reaction forces acting on the spring. This is for spring number 1, the reaction force acting at the left end of spring number 1, and this is the reaction force acting on the spring and rightmost spring on its right node, or right degree of freedom rather. And these were the applied forces. So these were the unknown displacements and these were known displacements. So where the displacements are known, the forces are unknown, and where the displacements are unknown, forces are known. And from here we actually took these two equations. So these two equations, because if you want to solve this matrix, first of all you will not be able to solve it because this matrix is singular. So you have to put the boundary conditions. So what we are taking, in place of taking these four equations, we are taking first these two equations, because these two displacements are your unknown displacements. So this is one equation and this is the other equation. In this equation this U1 is 0 and in this equation this U4 is 0. So this is the equation where we are taking this term in the right hand side and this term in the right hand side, and so this is the matrix equation. And since these U1 and U4 are zeros, so these two terms need not be considered and we get this final equation. So you solve this and you get the results. So this method of incorporating the boundary conditions is known as the row column deletion method. So what we are actually doing, since the displacement at the first degree of freedom, that is U1, and the displacement at the fourth degree of freedom are specified, we are deleting the first row, the fourth row, the first column and the fourth column, and the remaining elements of the system stiffness matrix we are taking like this. And when these displacements are specified as zeros, the right hand will remain same. But when these specified displacements are non-zeros, which we will study in our next example, a case where this U1 and U4 are non-zeros will be studied in an example. So when they are zeros, then the right hand side will remain 10, 20. But when they are non-zeros, then the right hand side will get modified. So here we need not modify our right hand side. So this is the right hand side. So this is the first method, that is the method of row column deletion, which we have already seen, and we solved this and we got the results. And there is another method, which is the penalty function method. where what we do is, this is the method 2, penalty function method. What we do, see here at the first degree of freedom, the displacement is specified. So we make the first diagonal element a large number. How large number? That I will come a little later. And the fourth degree of freedom is specified. So at the fourth diagonal, you put a large number. And in the right hand side, since the first degree of freedom is specified, the displacement at the first degree of freedom is specified, the force at the first degree of freedom will be that large number into the value of the specified displacement. The value of the specified displacement is 0 in this case. So here we put 0. And in the fourth degree of freedom, since this U4 is specified, in the right hand side we put large number into U4 specified, and in this case it is 0. So you can think of this method like this. So these were our origin. This was our original problem where this node was fixed and this node was fixed. So instead of fixing this, we remove this support and put a very stiff spring here, and we put a very stiff spring here. So if this spring stiffness is very high, this node will move very little and it will be almost like a fixed support. And if this node is having a very high stiffness, this node will also not be able to move. So your problem is replaced by this. Now if you replace this by this, then if you look at the equilibrium equation of this node, suppose this node is having a displacement U1, so the spring force on this node will be LU1 in this direction, and this F11 is coming from this element on this node, and we are applying an external force LU1 SP here. So this is what we have done. We have put an external force LU1 SP there, but in this case it would be 0. And if you write the equilibrium equation, that is minus LU1 minus F11 plus LU1 SP equal to 0. And you know that F11 is nothing but this. So this is the equilibrium equation. That means ultimately you are getting this equation. And since this L is very large compared to this K1, finally you can write LU1 or LU1 minus K1 U1 equals to L U1 SP. So that is what is happening. LU1 minus 1000 U2 equal to L U1 SP. And the idea behind this penalty function method is, since this L is very large, so L into U1 will be larger compared to K1 U1. So approximately L1 L U1 should be equal to L U1 specified. So U1 should be equal to U1 specified. So this is the idea behind this. And when the displacement is 0, this is 0 and this is 0. So it is a spring of very high stiffness. So this node cannot move, this node cannot move. So this is the idea behind the penalty function method. So what we do, we put a large number at the diagonal of that row where the displacement is specified. So how to incorporate boundary conditions? One is method 1, row column deletion. One is method 2, the penalty function method. In row column method, the results are accurate, and because we are considering the actual equations, but the programming is difficult because you have to take the slice of the matrix accordingly. Here the programming is easy because the original system stiffness matrix remaining same. You are only putting large number at specified places, and in the right hand side you are putting the forces. So the programming is easy, but result may not be so accurate because here you are approximating. You are not taking the actual equations, you are taking approximate equations. So just like previous problem, we take a problem where the left node is fixed but the right node is having a displacement of 0.001 meter. So that means this system of spring, you pull it by 0.001 meter, that is 1 millimeter. So this node is not fixed like before. This node is having a specified displacement. So here in this equation, u1 is 0 and u4 is 0.001 meter. So if you do the method of row column deletion, then what would you do? You simply first row gone, fourth row gone, first column gone, fourth column gone, this remains. So this into u2 u3 equal to 10 20, but there will be a modification in the right hand side because this u4 is non-zero. So in this equation this 3000 minus 3000 will get multiplied with this u4. So but u1 is 0, so this term, this 1000 into u1 term will also be there in the minus 1000 into u2 minus 1000 into u1 term will also be there here, but this term has no meaning since u1 is 0, and this is the second term which is coming for minus 3000 into u4. So we take it in the right hand side and you modify the right hand side. So the right hand side is 1023. Now you solve and get this result in using some MATLAB or Octave or whatever. And in the method 2, that is the penalty function method, you put L here, large number, you put L here, keep this as it is. Here you put L into 0, so 0, and here you put L into 0.001. Now you take, suppose you take L is 10 to the power 8, then here you have to put 10 to the power 5 and here 0, and you solve this 4 by 4 equations and get the results. So we'll just show this thing to you using Octave. So let me open Octave. It will take a little bit time. It will open. So these are the actually two methods for incorporation of boundary conditions. This method is programmatically simple, but the other method is the row column deletion method is programmatically a little complicated. So this is our Octave main screen, and here suppose you know how to create matrix. So this is the first matrix we are creating, k equal to, I have shown you, this is 1000, then the next term is minus 1000, then 0 0. This is the first row. Then the second row is obviously minus 1000 and maybe 3000 coming here. So here minus 2000 and then 0. Second row over, and in third row 0 minus 2000 and then 5000, then minus 3000, then 0, and the fourth row 0 0 minus 2000, 3000. So we have made some mistake. So let's see. 0. Oh, here there were 1 2 3 4. So this semicolon is in the wrong place. So sorry. So it should be here, and just so this is the stiffness matrix. So 1000 minus 1000 minus 1000, 3000 minus 2000 minus 2000, 5000 minus 3000. Oh my god. So this should be minus 3000, I suppose. So you just modify like this, that K 4 3, isn't it? So 4 comma 3 is not minus 2000 but minus 3000. So if you put, so I think now it's correct. We'll check it once again. So this is 1000 minus 1000 minus 1000, 3000 minus 2000 minus 2000, 5000 minus 3000. So I think it's okay. It's okay. So now if you wish, the K matrix, you can check the determinant. So this is the determinant. It's a very small number. It should be 0. But we made some mistake. It should be 0, but it's coming small number. So determinant is a very small number. So on the right hand side, f equal to, okay, so now what you can do is you can take a slice of this matrix. You can take a slice of this matrix like this. Better. I am trying to make the screen smaller. Window, show command history, show browse, show workspace. This is what I want. Okay, because the answer thing was not clearly visible. Okay, now now suppose we write k new. So k new is equal to slice of k, that is k 2 to 3 comma 2 to 3. That means here what we are doing, we are taking the row from the second to third and the column we are taking from second to third. So that means this sum is, so this is this first 4, second row, second column, second row, third column, third row, second column, third row, third row. And the right hand side say f new or whatever, f new or f. So f equal to, you put 10 and 23. So, and you solve k new. So this, and you get the solution. So this is, I told you in the last class, this is k new inverse f. So if you want to remember, you can remember it like this, but it does not calculate the inverse. It uses Gaussian elimination, because inverse, for solution of equations, the calculation of the process of calculation of inverse is prone to having numerical errors. So generally people do the Gaussian elimination and then they get results like this. So this is the solution. So here I have written the solution. So this is the solution. Now if we implement the, or if we use the penalty function method, then let's see what happens. So k is this, and suppose we take a large number as say 10 to the power 8. This is a large number. So we put k 1 1 as capital A. So this has become K matrix. K matrix has become like this. So we should have avoided, we should have used some other name anyway. So K 4 4 equal to L. So this is the K matrix. Now some F2 let us form. So F2 would be some first 0 because you specified is 0. Then second column is 20. The third one is 10 20 10. Then 20. Then this is L multiplied by the specified displacement. So this is L. And now if you do the same process, F2. So these are the displacements you are getting. See, you are getting approximately 0 at the left end and approximately 0.001 at the right end, and these are the displacements at DOF2 and DOF3. So now if you use L equal to say 1E9 and you use, as I told you, the upper arrow key is used to get the previously used commands. Okay, now if you solve, so this is the solution. See, it has improved. Previously there were 1 2 3 4 5 6 7 zeros, and now there are 1 2 3 4 5 6 7 8 zeros. So this term has gone towards more towards this term is more towards 0, and this term is might be more. If you compare, you can understand this term is, so 3 zeros here, now there are 4 zeros here, so this term is more towards 0.001. So I have written down the solution. So 10 to the power 8, 10 to the power 9 and 10 to the power 10. But you cannot indefinitely keep on increasing the large number, because slowly the numerical problems will creep in. If this L is very large compared to this, then slowly the numerical errors will creep in. So you can keep L say 10 to the power 7 times larger than the highest element here in the matrix, 10 to the power 7, 10 to the power 8 times the largest element present in this system stiffness matrix. Then it will run okay. So these are the two methods which for incorporation of boundary conditions. So thank you.